Okay, Unit 8, Target 2, talks about angle bisectors and angle bisectors in a triangle. So, any point on an angle bisector is equidistant from the sides of the angle. That's a theorem. So there's an angle bisector as shown by the red congruent marks there. And if I measure the distance from a point to a line, I have to measure it as a perpendicular distance. So if I draw from a point on the angle bisector to the sides of the angle, I create two triangles that are congruent because of angle, angle, and then side with that reflexive property. So because the two triangles are congruent, that means that their corresponding parts, like these two blue distances I just drew, have to also be congruent. So we know that any point on an angle bisector is equidistant to the sides of the triangle. The converse is if a point is equidistant from the sides, then we know it's on the angle bisector. So here's some examples. Number 1 says find the measure of GFJ. GFJ is right here. And so I can tell from these 7s on the side that J is the same distance from G as it is from H. That means that J is on the angle bisector of the big angle GFH. So if one of those angles is 42, the other one is also going to be 42. For example, number 2, we are told down at the bottom by angle Q that this is on an angle bisector, or that SQ is an angle bisector, or QS as a ray. That means that point S, since it's on the angle bisector, is the same distance from sides QP and side QR. And since it's the same distance, we can say 5x equals 6x minus 5 and solve that for x equals 5. The last question, number 3, says why is B not on the angle bisector? Well, I can see that one distance from B to this side, let's say B to A, is equal to 2. And B to C as a perpendicular distance is equal to 5. And since those are not congruent, those two triangles we can see are clearly not congruent. And so it is not an angle bisector. Now, if you take the angle bisectors of a triangle and you draw the angle bisectors, you'll have 3 of them. They intersect at a point called the incenter. It's called that because it's the center of the circle that is inscribed in the triangle. And the incenter is equidistant to the sides of the triangle. So for example, if I kind of outline one of my angles, okay, that angle that I just outlined in pink has an angle bisector. I'm going to make the color match and the side size. There we go. So there's my angle bisector. So if a point's on this angle bisector, then it's equidistant to these two sides of the angle. Those are the same length. Well, if I pick a different angle and I bisect a different angle, let's use green this time. Then my angle bisector for the green line, again, I'm going to make that be the right size and color. If a point is on that second angle bisector, then it's equidistant from its two sides. So the first one on the left is already drawn, the second one on the right. And so now I have these 3 angle bisectors creating these segments that are drawn to the sides. So the center of the circle shows that the center is equidistant from the sides of the triangle, all 3 sides of the triangle. And so we could do problems like this. I drew my angle bisectors in red, and I drew the lengths to the side as a perpendicular distance in green. So angle GCA, GCA is this angle that I just marked in blue. That's going to be congruent to angle GCB. Angle GEC, GEC is a 90-degree angle. And so it could be congruent to any other 90-degree angle, like GDB. Angle ABG, I'm going to outline that one in pink. ABG, that angle is being bisected, so it's congruent to angle DBG. And then the last part says CD, or GD. GD is this perpendicular distance to the side, so it's going to be congruent with all of the perpendicular distances, such as GF and GE. And that's it for target 2.